Imagine an investigator who walks into a crime scene and decides it's a standard robbery. They ignore the muddy footprints. They ignore the shattered window. They have a strict, rigid idea of crimes and force every clue to fit. Now imagine the opposite investigator, one who obsesses over a tiny speck of dust, a dropped pen, a slightly crooked painting. They connect every random detail, building a wild conspiracy theory just for this one room. In machine learning, the first investigator represents a high bias model. Look at this bare data chart. It draws a rigid line, ignoring the pattern. The second is high variance, drawing an erratic path connecting every point, overreacting to noise. For a machine learning model to survive in the real world, you have to find the mathematical balance between these two opposing forces. That balance point is the core goal of machine learning. We call it generalization, the ability of a model to perform accurately on data it has never seen before. To measure how well a model generalizes, we need a way to score its mistakes. The most common metric is mean squared error. If we break down a model's total error mathematically, it splits into three distinct components: the bias squared, the variance, and the irreducible noise in the data itself. Adding more parameters to a model increases its complexity, and that directly alters those error components. Let's map it out. We'll put model complexity on the bottom axis and error on the vertical axis. As we increase complexity, the model becomes more flexible and less rigid. The bias drops significantly. But that flexibility comes at a cost. The model becomes overly sensitive to the training data, so the variance starts to shoot up. When you combine the dropping bias and the rising variance, you get the generalization error. It forms a distinct U-shaped curve. So what happens if we scale our model from 2 parameters all the way up to 100? Which error drops and which one spikes? By adding all those parameters, the bias goes down, but the variance explodes. Pushing complexity past the bottom of that U-curve, the sweet spot, guarantees the model will fail in the real world, even if it looks perfect during training. If you spend time reading AI literature, you'll quickly notice that the word bias gets thrown around in 2 completely different ways. Look at this plot showing a horizontal line passing through a cluster of height and weight data points. The model is too stiff for the data distribution. This is statistical bias, a strict mathematical rigidity or underfitting. That is separate from societal bias, which happens when an AI system produces discriminatory outcomes or relies on data that misrepresents certain populations. Fixing statistical bias is a math problem. You adjust the model's capacity. Fixing societal bias is a human problem. You have to audit the quality and fairness of the data itself. A successful model identifies the room's underlying geometry. Focusing on the specific furniture causes the system to fail the moment a chair is moved. Have you ever built a model that looked brilliant in testing, but failed on new data because it memorized the training set? Tell us about it in the comments. When a model builds a conspiracy out of noise, it has crossed into the most common trap in data science: overfitting.